In this final teaching unit of Introduction to the Design of Urban Drainage and Sewerage Networks with EPA-SWIM, we will eventually see how to configure our computational notions, what kind of calculations the software can do, and how to see the results of our first simulation. We will therefore explore the different typologies of flow routing computational methods: kinematic and dynamic wave routing, computing options and settings, and last but not least, we will visualize our first results through the software tools. The software can use 3 different computational methods: steady flow routing, kinematic wave routing, and dynamic wave routing. Which are the main differences amongst the 3 methods? Well, to start, we can imagine that the steady flow routing is rather a simplified method of calculation. Steady flow routing does not generate any temporary delay, and it does not consider any entrance or exit losses, backwater effects, or reverse flow routing. It is a fast calculation, but it should only be considered as a very preliminary analysis, and it is only suitable for dendritic networks and not for mesh-shaped networks. It only admits one single outflow link for each node in the network, and this calculation will not admit outlets, orifices, or weirs. It will permit dividers, and outfalls will be considered as junctions. Another more developed computational method, allowing for a non-steady flow routing, is the kinematic wave routing. Calculations are based on Saint Venant's equations, though some of the equation terms are not considered. This method will take full consideration of flow peaks and overflooding. It can only evaluate dendritic and rapid-flowing networks that are not overflooded. It is a very fast calculation methodology, and it is more stable. In fact, the simplified formulas make the whole process much faster, and results converge in a clearer way. This method does not admit regulators such as outlets, orifices, or weirs, since these elements are only permitted in the dynamic wave routing method, whose mathematical model admits pressurized elements. But kinematic wave routing does not contemplate dividers. Outfalls are considered as junctions. This method is only efficient if our network is dendritic and there is no excess flow in the conduits. Therefore, we need to be sure of the layout and conditions of our network to make the right decision when choosing the kinematic wave method. If we're not sure whether the kinematic wave routing is a suitable method, we will choose the dynamic wave routing, described in the next slide. The dynamic wave routing can solve the complete one-dimensional Saint Venant's equations. Gravity, friction, inertia, and pressure are taken into account. These are the forces naturally present in a drainage network. Therefore, this method is undoubtedly the closest one to reality. Because all these forces are contemplated, this method permits a full closed conduit flow as well as overflooding. However, mathematical formulations are more complex, and this can lead to unreliable calculations in complex water flow situations. All of this leading to completely wrong results. Therefore, we must carefully check that results are valid, unique, and consistent with the value we are looking for. If this is not the case, in order to overcome this possible phase, the software provides different options. The first and most common is to reduce calculation intervals. Equations are more likely to converge with shorter calculation intervals, such as 1 second to 10 seconds intervals. Since we will not use minute-long intervals, which were permitted in the kinematic wave routing method, the first thing to consider for us is that intervals must be short. If, despite all of this, our results do not converge, we will keep shortening our intervals. Then the software will allow us to ignore or to ponder the inertial terms. These are the options called dampen or ignore. Inertial terms in St. Venant's equations may lead to non-converging results, and pondering or ignoring certain results can help us converge to a certain value. The dynamic wave routing obviously accepts all flow regulators, such as outlets, orifices, weirs or pumps, but it does not admit dividers, which, in this case, act like junctions. They do act like junctions because in the dynamic wave routing, the flow distribution, whenever the junction splits in two, is not defined anymore by the dividers parameters, but rather by the St. Venant's equations. And these equations set for all the elements how flows are divided, where they go, and how many outlets a node has. In this slide, we can see the aforementioned St. Venant's equations. There is the continuity equation and the momentum equation. In the case of kinematic wave model, only the continuity equation will apply. Whereas for the dynamic wave model, both the continuity and the momentum equations will apply, since the latter includes terms for inertia, acceleration, pressure, gravity, and friction. Inertial terms are those terms that can be ignored or pondered in order to make these equations converge. Well, now that we have explored all the visual and non-visual objects in our network, now that we have gone through the formulation used for subcatchments in the hydrological model, and now that we have reviewed the different types of formulations to calculate flow routing inside our network, we can define the calculation options we need in order to proceed to our first simulation. There are 5 different tabs in the window called Simulation Options. The first tab, General, shows the processes we want to model. That is, rainfall, runoff, snow melt, groundwater, flow routing, or water quality, as well as other calculation and reporting options. We can also include the minimum slope at conduits, and in this case, we will select one of the 3 infiltration models of our network and the hydraulic calculation method, which is steady flow, kinematic wave, or dynamic wave. We can also select the infiltration model through Horton, Greenamt, or the curve number of the Soil Conservation Service. The second tab is the Date tab. We will here set the date and time our simulation starts, as well as the starting date and time for our reporting, the end time of our simulation. If we are using the quality model, we will set the starting and the end date of street sweeping, as well as the record of dry days in the system. In the Time Steps tab, we will visualize the different time steps to report presentations, dry weather periods, wet weather periods, or in other words, when precipitation is affecting our system, and the routing time step or routing period. This routing period greatly depends on the chosen calculation model. Obviously, it is pointless to calculate a routing period when we are in a steady flow model. For kinematic wave routing, the routing period will be minutes. Now, if we are in the dynamic wave routing, this routing period will be seconds. Otherwise, Saint Venant's equations will not converge and results will not make any sense. This routing period will be adjusted to our network so that results converge and so that the simulation can be as fast as possible. Therefore, we will keep a routing period as long as possible within our converging results. In dynamic wave routing, the tab called Dynamic Wave helps us decide what to do with inertial terms, define how the formula behaves in the case of supercritical flow, define the integration method in the formulation, time step variability, and enlarge time steps in conduits to make results converge. Finally, we will also define the minimum surface area at node. All these options obviously require full knowledge of continuity equations and all of Saint Venant's equations. Only then can we operate in this user interface and personalize the dynamic wave routing model to obtain as stable as possible results with as long as possible routing periods. We would like to remind here that the goal of this introduction model is in no way to go into further detail and get deeper knowledge of all these parameters. Now to finish, the Files tab will only be activated if we want to add files to our project, but this is not the case in this introduction. Once our simulation options have been configured, once our network has been properly defined from a hydraulic and hydrological point of view, we are ready to carry out our first simulation. So let's click on the simulation icon and let's run it. If you can make it at the first attempt, congratulations! Because the first time, honestly, it is more than usual to find an unexpected element which will make us review the whole simulation. That is why we will resort to reporting and warning messages from the storm water management model to see where errors occurred and where we have to correct some data in the project and start the simulation over. We will repeat this process as many times as necessary until our simulation is successful. And once it is, here is what we shall do. Once we have our first simulation, we must check that results correspond to those we can expect as engineers. Therefore, before validating our project and results, we will have to visualize them, and we will use the different tools available in the software to do so, and to be certain that the results are the ones we wanted. Or perhaps, to reach that conclusion, we will have to modify some entered data and make some adjustments to guarantee that our simulation meets our expectations. In this last slide, we can see the different types of visualization once our simulation has been completed. We can see the status reports, results on a map, results using graphs, time series plots, profile plots, scatter plots, results in a tabular format, and statistics reports. And this is the end of this teaching unit of Introduction to the Design of Urban Drainage and Sewerage Networks with EPISWIM, in which we have seen the software calculation options and the visualization of results once the simulation has been completed.